Stanford University.
Okay, the last time I explained to you Schwarzschild coordinates for a black hole. Let's go over it. And tonight, I want to show you how you can think about the formation of a black hole, a real black hole, and how much of this Schwarzschild story, the diagram we drew on the blackboard last time, really is physically meaningful. Not all of it is. Okay, so the last time I showed you that the geometry, the metric of a black hole, of a Schwarzschild black hole, has the property that very near the horizon, that's the horizon over there, it looks like flat space. The horizon is a kind of polar coordinate, a hyperbolic polar coordinate point, similar to the behavior of accelerated coordinate frames. Somebody standing outside, and this wedge over here, this quadrant over here, is outside. The rule is, first of all, that 45-degree angles represent the motion of light rays either going in that direction or going in this direction. Somebody outside the black hole means out here in this quadrant, and quadrant, let's label them. Quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And as we're going to see, quadrant 3 and quadrant 4 really don't have any physical significance for a real black hole. It's quadrant 1 and quadrant 2 which have real significance. Outside the black hole, somebody at rest, outside the black hole, somebody at rest, of course, is experiencing a sense of acceleration. Just as I'm experiencing a sense of acceleration right here. I've gotten used to it, so I don't notice it, the fact that I'm being accelerated. But if somebody who had been in outer space too long, in free fall too long, lost the sense of what a gravitational field is like, and you plunk them on the surface of the Earth, they would be experiencing a sense of upward acceleration. And in fact, in this diagram, somebody at rest does appear to be accelerating away from the horizon. Come in and go out, and it's that acceleration which is what we experience as gravitational acceleration near the surface of the Earth, but in this case near the horizon of the black hole. So this is a family of observers further and further out, very far from the black hole, way out here. In close to the horizon here, the closer you get to the horizon, the more you have to accelerate. That's the curvature of these lines here. The more you have to accelerate to keep out of the black hole. And in any case, this is the exterior. The lines of constant time, they look like this. The red lines are lines of constant position. The green lines are lines of constant time. And they accumulate up near this blue line up here. So this is t equals 0, t equals 1, t equals 2, t equals 3, and t equals infinity is way, way up on this 45-degree surface here. So that's the outside of the black hole. And the inside of the black hole is quadrant number 2. In quadrant number 2, for a real black hole geometry, not for flat space, but for a real black hole geometry, there's something nasty. And the nasty is the singularity. And the singularity looks like this. I don't know what it looks like because I've never seen one, but it's a bad place with lots and lots of tidal force. Okay. And the problem with it is once you find yourself in quadrant 2, there's no way out. The only way to get out, even if quadrant 3 was meaningful, which it is not, but even if it were meaningful, you can't escape from here to out here or to out here without exceeding the speed of light. Your trajectory somewheres has to have a direction which is shallower than 45 degrees. And that means exceeding the speed of light. So that means if you don't exceed the speed of light, the only place you can wind up is somewhere on the singularity. So you're doomed. If you're outside and you make a bad mistake, you could fall in. But if you don't make a mistake, you can jump back out and get out. So people on the outside, or light sources on the outside, flashlights, whatever you like, they can produce signals which go in, or they can produce signals which go out. And that's the character of a black hole. Okay, so that's all there is to black holes. The geometry is somewhat warped. It's not just flat space. It's somewhat warped and curved, but this is basically it.
Could you say what the axes of that diagram are?
Time and space. Time and space as seen by an infalling observer.
And so the lines of constant position that you drew are for what, a stationary observer outside?
Yeah, that's correct. So for somebody falling in who doesn't accelerate, the coordinates that they see, which are not too different from ordinary flat space and free fall, at least until they get near the singularity, time and x, those are the coordinates that such a person would use. Okay? Right. And so to them, the space looks flat, pretty much, especially near the horizon over here. To somebody on the outside, they experience this acceleration. And the acceleration is basically the same as the accelerated reference frame in flat space. Okay, now, it's very convenient to redraw pictures like this. Space is infinite here. It goes on and on and on and ends up somewhere in the next county or further than that. And time may come to an end at the singularity over here, but these directions off at 45 degrees, these light-like directions, they are also infinite. And so I can't draw the entire space-time on the blackboard. For many purposes, it is useful, convenient, provides some visual tools, provides some intuition to be able to draw the entire space-time on a finite piece of the blackboard. Well, you can imagine why. You want to see everything that's going on. You want to get a complete overview of space-time. You'd like to draw it on the blackboard in some finite region. Okay? Let's start doing that, but let's start with flat space. Let's start with good old ordinary flat space and take all the flat space-time. When I say flat space, I mean flat space-time. And let's redraw it or re-coordinatize it so that we do a coordinate transformation which pulls the whole thing into some finite region on the blackboard. I'll show you how to do that. This is useful, incidentally, for geometries, spacetimes which have rotational symmetry. Rotational symmetry means they're the same in every direction. They mean the same thing rotational symmetry is when we say a gravitational source has rotational symmetry. It means the same in every direction. And when a system is the same in every direction and has rotational symmetry, it's usually useful to describe it. Now I'm talking about ordinary polar coordinates. When a system has rotation symmetry, it's the same in every direction, we don't care so much about the angle. Everything is the same independent of angle. What we care about is how things vary as we move away from the center, the radial direction. And so for many, many purposes, we don't need to think too much about the angular direction. And we just think of space-time, flat space-time, ordinary flat space-time, as having a time axis. That's the time axis. It goes from minus infinity to plus infinity. And it has a radial direction. The radial direction is like that. The radial direction never gets negative. R is never negative. In polar coordinates, R is always positive. And so the entire space-time is to the right of the time axis here. Only because being to the left of the time axis would mean negative r, and r is always positive. It's distance from the origin. So here's everything, the entire space-time. And let's put some markers on it to be able to visualize some landmarks. First of all, this horizontal axis is t equals 0. That is t equals 0, right over there. Let's put in t equals 1. T equals 1 looks like this. T equals 2 looks like this. T equals minus 1 is like this. T equals minus 2 is like this. And if I wanted to draw the entire set of possible times, it would take me up to heaven and down to hell. Okay, so this is all possible times. And we could also plot all possible radial distances, and the radial distances would just look like this. This would be r equals 1, r equals 2, r equals 3. And in all cases, I will imagine using units so that the speed of light is 1. C equals 1. That simply means that I work in, if I'm going to use seconds for time, I use light seconds for distance. And then light rays will move at 45-degree angle. Well, that's not quite right. Let's think about the motion of light rays. If a light ray, let's draw another picture over here. Here's r equals 0. This is polar coordinates. This is the radius here. It's just one instant of time, looking and including the angle now. If a light ray comes in radially toward the origin, it hits the origin, and then what does it do? It goes back out. I meant to draw it straight, but this is just saying that a light ray in polar coordinates that happens to be aimed directly at the origin from far away. Imagine it's coming in from very far away. If it happens to be aimed right to the origin, it will go to the origin and then go back out. On this diagram, it will appear to bounce, to reflect off the origin. Here's r equals 0. This is r equals 0 over here. And so a light ray coming in from long in the past would look like, I think I'll use another color. A light ray coming in from the past will look like this. Moving at 45-degree angle, it will get to the origin at some time, and when it gets to the origin, it will simply start back out. It hasn't really reflected off anything, of course. It has just gone through the origin, came in, and went back out. So a light ray starts out in the very remote past, coming in at 45-degree angle from a place that we call light like infinity, past light like infinity. But all it means is the place where all light rays come from in the infinite past. And they go out to the infinite future. Of course, there are other light rays that do the same thing. This one comes in a little bit earlier and goes out a little bit earlier. Another one up here. But they all look pretty much the same. They come in at 45, they bounce off the origin, and they go out at 45 degrees. Now, just for fun, let's think about a light ray which doesn't pass through the origin. A light ray which doesn't pass through the origin will miss the origin. It comes in and it misses the origin. When it's very, very far away, you can't really tell that it isn't, unless you have very good precision, angular precision, extremely fine angular precision. Watching that light ray way, way back there, it's hard to tell whether it's going to hit the origin or not. So it starts out coming in pretty much the same way. But it never gets to the origin. In fact, it almost appears to be repelled away from the origin and then goes back out. That repulsion, it's not a real repulsion, but it is what we call centrifugal force. It really is centrifugal force that keeps the light ray from hitting the origin. Or you can just say it doesn't hit the origin because it wasn't aimed at the origin. Same thing. But what does it look like? It comes in pretty much the same way at first, and instead of going through the origin, it gets a point of closest approach, The closest approach is over here, and at that point, it starts going back out. So a light ray which is perfectly radially tuned to hit the origin looks like a 45-degree ingoing and outgoing line. But a light ray which misses the origin looks like, in fact, sort of like, it looks like a hyperbola. But whatever it looks like, that's it. I'm just telling you these things here to give you some landmarks and to give you some perspective on what we're going to do next. Next thing, we're going to take this diagram and we're going to squeeze it and stretch it in various ways to get the whole thing on the blackboard. That's going to deform it. It's not going to look the same, but we're going to keep one thing fixed. The one thing fixed is that light rays will always be assumed to move on 45 degrees. In other words, any squeezing and squashing and stretching that we do should preserve the fact that light rays move in 45-degree angles. That's a useful thing to do because then we can see how light rays move. And we can see what going faster than the speed of light, what going slower than the speed of light looks like. So I'm going to show you how to do that mathematically.
Excuse me.
Yeah.
There's nothing special about the origin. There's not a black hole there or anything.
No. At the moment, there's nothing special. It's just a particular point that we may want to focus on. There may be something there, but no need for it.
Okay,
It's
so
just
the light rays in this diagram are bent just because of the particular way that we've chosen.
Yeah, that's right. It's just a choice of coordinates at the moment.
Okay.
Now, there may be good physical reasons to want to use a particular choice of coordinates. In studying the sun, there is no black hole, but the symmetry of the problem makes it convenient to think about the sun as being the center of something, and right. So that's all we're doing. All right, next step. Let's assign some coordinates. I'm not going to call this T. I'm going to give it another name. I'm going to call the vertical axis capital T, and the horizontal axis capital R. I don't want to confuse them with other T's and R's that we're going to use and that we have been using. So we're going to call it capital T and capital R. But there's another way to coordinatize this, and that's to use coordinates at 45 degrees angle. In other words, to introduce axes along 45-degree angles here and here. Of course, I don't mean to imply that there's anything behind r equals 0. We're only interested in this region here, but we're going to introduce new coordinates, and this coordinate over here, that's not going to be t or r, it's going to be t plus r. T plus r varies as you go from here to here to here. And if I were to plot constant t plus r would be these lines. Oops, I didn't draw it well. Let's draw another picture over here. R, T, constant t plus r will look like this. These will be the lines of constant t plus r. Okay, so there's t plus r, and of course, there's also t minus r. T minus r, the lines look this way. But really, we're only interested in this half over here. So the lines of t minus r, constant t minus r look like that. These are useful coordinates, as we'll see. T plus r, that's called t plus. T minus r is called t minus, just as you might expect. Okay, so we have a different way of describing the same space-time, the same flat, good old flat space-time. Instead of t plus r and t minus r, we have t plus and t minus. Now, what about this line here? What was this line? This line was just plain r equals 0. R equals 0. Okay? So, what is that? What is r equals 0? That's t plus equals t minus. So let's write t plus equals t minus. T plus equals t minus That's the same thing as t plus r equals t minus r, or r equals minus r. The only solution to r equals minus r is r equals 0. So this line over here, which was r equals 0, is also just t plus equals t minus. That's a way to describe it. Okay, now we're going to change coordinates. And the way we're going to change coordinates is to introduce two new coordinates. These are called light-like coordinates. T plus and t minus are called light-like coordinates. We're going to change light-like coordinates. We're going to introduce two new light-like coordinates. One of them is called u plus, and one of them is called u minus. And u plus is a function of t plus. So we're going to write u plus is some function of t plus. It's not going to involve t minus at all. And u minus is going to be, in fact, I think the same function of t minus. All right, but this function is just a coordinate transformation in which u plus and u minus independently, t plus and t minus just independently transform to some new coordinate. Okay. Good. What kind of function am I going to use? I'm going to use a function of t plus. This is f, or u, this way, u equals f of t plus. And the function is going to look like this. When you go out to t, it doesn't ever become absolutely flat. It's always got a slight positive slope. Also, down here, it also has a slight slope. All right? But it'll go to 1 over here, u plus, this is u plus of infinity is 1, and, or just f, let's call it f. F of infinity is 1, and f of minus infinity is minus 1. Now, anybody know a function that does that? There are many functions which do that.
Hyperbolic tangent, is that it?
What's that?
Is this a hyperbolic tangent?
Yeah. A hyperbolic tangent is the one that's usually used. Hyperbolic tangent goes to 1 asymptotically. It's the usual one that's used, but there's nothing special about it. Hyperbolic tangent, f of t plus is, and if you don't know what a hyperbolic tangent is, don't worry about it. It's just a function which looks like this. Tanh of t plus. Okay, now think about what happens as we start moving on this graph further and further outward. T plus is getting bigger and bigger and bigger. What is u plus doing? It's never going to get bigger than 1, right? It's never going to get bigger than 1. So let's draw our same space-time with these new coordinates. I think I erased them, but let's put them back. U plus equals hyperbolic tangent of t plus, and same thing for minus. As we move out, let's redraw our picture. As we move out, let's start over here and move out. How big does u plus ever get? U plus never gets bigger than 1. So this diagram, if this is the u plane, not the t plane, but the u plane, u plus never gets bigger than 1. Here it is, right there. It never gets bigger than 1. So that means all of the space-time has been mapped somehow down into here. Okay. What about u minus? U minus is equal to hyperbolic tangent of t minus. What this says is as we move down in this direction, t minus never gets bigger or less negative than minus 1. T minus is getting very, very big and negative as you go down here. T minus is getting bigger and bigger but negative as you go down here. But U minus sort of maxes out again at -1. And here's T minus equals -1. T minus never gets too far. T plus never gets too far. This is, no, I'm sorry. I said T plus and T minus never get very far. I meant U plus and U minus. U plus equals 1. This is U minus equals -1, in fact. And what about this vertical line here? The original vertical line over here was T plus equals T minus, right? T plus equals T minus, that's the same as R equals 0. If T plus equals T minus, then that says that U plus equals U minus. So in fact, this line happens to be U plus equals U minus, and it looks like a vertical line. All we've done, if you don't follow the details, all we've done is squish the geometry this way, squish the geometry that way, and squished it onto a finite triangle. You'll understand this better when I draw in these coordinates. Okay? Now, what is the trajectory of a light ray, an outgoing, let's say, an outgoing light ray in terms of the T pluses and the T minuses? Well, an outgoing light ray is at a constant value of which, T minus, I guess. T minus would be constant and fixed on here. T plus would be constant and fixed for an ingoing light ray. But if T plus is constant and fixed along some trajectory, it means that U plus is constant and fixed along that trajectory. Likewise for T minus and U minus. The upshot is that if you make a coordinate transformation like this, it is still true that radial light rays move on straight 45-degree angles. These are light rays that come in from the remote past, bounce off the origin, and go back out. Again, bouncing off the origin is just a figure of speech. You just pass through the origin. So we've succeeded in taking all of space-time and mapping it to a triangle that we can draw the whole thing on the blackboard. Let's draw in some more coordinates. Let's draw in more detail. In particular, let's take these horizontal slices which correspond to different times. Let's imagine starting at the origin at, where's t equals 0? Here's t equals 0, and moving outward, outward, outward. We'll allow ourselves even to exceed the speed of light and just move outward in our imagination. What does that look like? That, of course, looks like starting at a point over here and just moving outward. And where do you eventually get to? You get to there. So, this point must be spatial infinity, r equals infinity. It's where you get to if you just walk along this line till you get out to infinity. But what about this line over here, t equals 1? If you plot that in these coordinates, it'll start about over here, but it will go to that same point. Likewise, t equals -1. So what we've done is we've squished all of spatial infinity. We've squished it into a point right over here. And it's called space-like infinity. Yeah.
Are those lines supposed to be straight? Or
no, they're not exactly straight. It depends, of course, on the particular choice of function, but they won't be straight. No, let's draw them more carefully. One of them will be straight. The one will be straight will be the t equals 0. This one will be straight. And then the next one will look like this. It'll have some curvature. What about way, way, way up there? T equals 100 billion. T equals 100 billion is going to be very close to this edge. So as we keep putting in more of these, they accumulate and get closer and closer to this edge up there. You've got to get an infinite number of them in there. Time really does go on and on forever, at least in flat space. And so this is what the series of timelines would look like, different times. On the other hand, now let's look at fixed spatial position. Fixed spatial position, we can mark off different locations. Here's r equals 1, here's r equals 2, r equals 3, r equals 4, r equals 5, dot, 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 and they again get all squished up near r equals infinity. Where do they all go? They all go vertically upward, and on this diagram, they all go up right up to this point up here. You can check that by doing the transformation, and that's what you would see. More and more and more of them. It's the same diagram, just in different coordinates. Okay? And in this coordinates, as I said, everything gets mapped to a finite region of space-time. Again, I emphasize light rays move at radial light rays move at 45 degrees, they come in and they go out, and so forth. Okay, this is called, this process of squeezing everything onto a finite piece of the blackboard without changing the speed of light. It's called compactification. You take everything and you compactify it. But it's also called making a Penrose diagram. This is a Penrose diagram of flat space-time. Roger Penrose. Sometimes it's called a Carter-Penrose diagram because a physicist named Carter, I think, actually invented it first. Brendan Carter. But it's usually called a Penrose diagram. Good. So that's flat space-time laid out on the blackboard. Now, the question is, supposing you took the black hole. Here's the black hole geometry. It also let's put, there's some names of points. This is called spatial infinity, or r equals infinity. This one up here, what would you call that? That's what you get when you just go vertically upward. That's time equals infinity. Right, use green. T equals infinity. That's this point. What about this one? That's t equals minus infinity. All right, so this, I'll give you the name. This is called future time-like infinity. This is called past time-like infinity. This is called spatial infinity, or space-like infinity. And what about these lines here, these 45-degree angles? These 45-degree angles are where all light rays come from. Light rays come in and go out. They don't really go out because it takes an infinite amount of time for them to get out. But a light ray beginning in the infinite remote past starts out its life coming in along one of these light-like trajectories here, bounces off and goes back out. The standard terminology is to call this script I minus, sometimes called scry minus, script I, scry minus, and I don't know why, I don't know where the I came from. I know what the plus and minus means. This is called I plus, or script I plus, and these are called past light-like infinity and future light-like infinity. The place where light rays begin and the place where light rays end. And that's the terminology. And that's what flat space looks like when compactified. Now, what about the black hole? The Schwarzschild black hole, what does that look like? We can do exactly the same thing. We can do exactly the same thing. Take this whole diagram, introduce again, I guess we can call this R, capital R, the original Schwarzschild coordinates. And we can again introduce light-like coordinates, t plus r and t minus r, do exactly the same operation. And what will we get? What it will look like, I'm going to draw it over here, and then I'll show you how it works. Okay, that's everything and the whole thing drawn on the finite blackboard, and I think you can probably see what goes where. The exterior of the black hole, that's this quadrant over here. This square, it's a square if drawn properly. And we can again draw coordinates. Here's t equals 0, here's t equals 1, here's t equals 2, here's t equals 3, t equals 4. That corresponds to these lines, which all pass through this point over here. They also pass through this point over here. The origin over here, which is the horizon, is right over here. Okay, what about the vertical lines, the red vertical lines? Those are constant position. Those are observers who are hovering above the black hole at a constant radius. They look like this. Way out, even further out, in closer. Here's somebody hovering close to the horizon. Here's somebody hovering very close to the horizon. The closer you hover close to the horizon, the more you have to accelerate to keep out. So it's not a comfortable thing to be hovering above the horizon because you're being pulled or jerked or whatever. You're being accelerated. This is the exterior of the black hole. What about quadrant 2? Quadrant 2 is over here. Quadrant 2 is over here, and it is the place where you're doomed. Here's the singularity. Now, the singularity is not off at infinity. It takes a finite amount of proper time to fall from the horizon to the singularity. It's a finite excursion from here to here. And so the singularity is a finite time away. Somebody who falls through doesn't get to experience an infinite time. They will hit the singularity. And this is it. Here it is. It's the whole thing, the whole black hole geometry laid out in a Penrose diagram. If you're over here, you're doomed. If you're out here, you can escape, or you may go in. Now, you should ask yourself now, what is this other half? If this is the outside of the black hole, what is this other half over here, and what's down here? What's down here in particular? What is this thing I drew down here? That's quadrant 3 and quadrant 4. Quadrant 3 and quadrant 4 have no real meaning for a real physical black hole, as we're going to see. We're going to work out a real physical black hole, but they really have no meaning. They're not really on the diagram of a real black hole. Nevertheless, you can ask what kind of geometry is described by this full, what it's called is the extended Schwarzschild diagram. It seems to have two exterior regions. A second exterior region over here, where you can escape outward in this direction, or you can fall in from this side. It seems to have two exterior regions connected together at the horizon. That's the horizon. That's the place where r is equal to 2mg. R equals 2mg, Schwarzschild r. Okay. Remember, it's the place where 1 minus 2mg over r changed sign. Whereas you came in, you suddenly changed sign and went off in a light-like direction. All right, so that's what it looks like. But supposing now we take a fixed slice here that looks like this, goes right through from here to here. All right. What does that space look like? It's space now. It's not space-time. Space on this green slice, or this green sheet surface. What does it look like? I'm going to tell you what it looks like. You start out way out here. And space is very big. Namely, the celestial sphere is very, very big. Way, way out here at large r. Okay? So, you see a very big region of space. I'm just drawing it as a plane. Right? As you come in, you move in closer and closer to this horizon. What happens to the radius of the sphere? It shrinks down to r equals 2mg. So you could draw that like this. It's getting smaller and smaller. That's not very good. I don't like that. I don't want to. Let's try to do better. Let's look almost edge on. And then as we come in, it shrinks down these circles. Okay, let's go back a second. Each point on this diagram represents a two-dimensional sphere. Do you understand why it represents a two-dimensional sphere? Remember, we're using polar coordinates. Right. So just as in polar coordinates on a plane, each radial distance represents a circle, each radial distance in three-dimensional polar coordinates represents a sphere. At each point here, there's a sphere that somebody could move around on, a two-dimensional sphere. Right? And the two-dimensional sphere is very big way out here. As you come in, the two-dimensional sphere gets smaller and smaller until it gets to some minimum size over here, and that's the horizon. That's r equals 2mg. Now, what happens if you just keep going on this diagram, on this sort of fake diagram, half of which has no real meaning? That we'll see. Well, it starts expanding out again. It starts expanding out again until it gets very big. It looks like you can pass through from one side to the other by going through what people call a wormhole. Okay? It's also called an Einstein-Rosen bridge. It connects two what appear to be external regions to the black hole, which get bigger and bigger and bigger as you move away from it. And it looks like the black hole is connecting two universes, two asymptotic regions. You might think, well, you could pass through, going from here to here. You can't. Let's think about somebody who wants to start on this side and wants to pass to this side. If they start out here, anywhere's on this side, and they want to pass to this side, their trajectory has to exceed the speed of light. There's no way to get from this quadrant to that quadrant, even if you start very, very long in the past and you're willing to go way up into the future here, you still have to exceed the speed of light. So in fact, this diagram is a little bit misleading. It's everything at an instant of time, but there simply isn't really time to go from one side to the other. You cannot go from one side to the other. And so the Einstein-Rosen bridge is not really a bridge. One way to think about it is that it opens up and closes again before anything can pass through it. But the best way to think about it is just to look at this figure and say, yeah, if you could exceed the speed of light and move horizontally, yes, you would move from here to here and going through the neck at the center there. But you're not allowed to do that. You can only move on 45-degree angles or less, and so you really can't get from one side to the other. This has been a source of all sorts of science fiction, passing from one universe to another through the center of a black hole, but as you can see, it doesn't happen. These kind of wormholes, or whatever you want to call them, which you cannot get through, they're called non-traversable wormholes, meaning to say you can't traverse them. You can't go from one side to the other. I'm sorry to disappoint you, but that is the way it is. But in fact, as we're going to see in a few minutes, the meaning of the left-hand side, there's no real meaning to the left-hand side anyway. There's no place to go. There is no real left-hand side. The left-hand side is really absent from here. So let's talk about now creating a black hole. Creating a black hole, not in the laboratory, that's too hard, but creating a black hole in infinite space by having some infalling matter. Okay? We're going to take very special kind of infalling matter. What we're going to do is imagine making a black hole. We start with no black hole. There's no black hole, but what we have is a very, very distant shell. It's not a shell made out of iron or anything like that. It's a shell of incoming radiation. somebody way, way far away created an incoming shell of radiation, a thin shell of radiation. Radiation carries energy, radiation carries momentum, and the shell is coming in. It's coming in with the speed of light. At some point, as we will see, this shell gets close enough together that there's so much energy in a small region that a black hole forms. All right, so this is the simplest version of black hole formation. A star isn't really made up out of things which fall in with the speed of light. This is the problem of a black hole being formed by stuff coming in with the speed of light on a thin shell. It's the simplest of all relativity problems. All right, so let's see if we can figure out how it works. You need to know really only one important thing, two important things. The shell moves in with the speed of light, and the other thing is a version of Newton's theorem. Anybody know what Newton's theorem is about gravity? For a spherically symmetric gravitational region? In particular, for a mass distribution which forms a shell. Supposing you have a mass distribution which forms a shell, it doesn't matter whether it's moving or doing anything. If you have a mass distribution which forms a shell for which there's nothing on the interior, then there's no gravitational field on the interior. The interior is completely without gravitational field. So if you have a shell of material, spherically symmetric, with nothing on the interior, there's a gravitational field on the outside. This is Newtonian. There's a gravitational field on the outside which is identical to a gravitational field of a point mass at the center, same amount of mass. But on the inside of the shell, there is nothing. So outside, it looks like a point mass. Inside, it looks like there's nothing. That's Newton's theorem, or a special case of Newton's theorem, that on the interior of a distribution of mass which forms a shell, you see no gravitational field. On the outside, you see the gravitational field as it would be if all of that mass was concentrated at a point. That's even true if the shell is moving. As the shell moves in, more and more space will look like the field of the point mass, and less will look like empty space. But interior to the shell, it always looks like nothing's there. Exterior to the shell, it looks like a point mass. This theorem is also true in general relativity. The statement of the theorem is if you have a shell of infalling or a shell of mass of any kind, then the interior region is just flat space-time, just as if there was no source. The exterior region, it doesn't look like the Newtonian point source. What does it look like? It looks like the Schwarzschild solution. So if you have, in general relativity, on the inside of a shell of mass, flat space-time, on the exterior of it, it looks like the Schwarzschild black hole, SCH, black hole. So if you had a static, non-moving shell, what you would do to construct the actual solution is you would sort of paste together an interior here which was flat with an exterior which is Schwarzschild. You do the same thing in Newtonian physics. Paste together, no gravitational field on the inside with standard gravitational point source on the outside, and that's the way you find solutions of Newtonian physics. You do exactly the same thing in general relativity. Okay, so now we can, let's redraw the rest of this black hole here for a minute. Let's put it back. I erased part of it, but I want to put it back. Okay, so let's go back up to here. Flat space-time. In flat space-time, I'm going to redraw it. I want to get rid of all these decorations and just put in nothing in space-time. But now I want to add the idea of an incoming shell of radiation. You can think of the incoming shell of radiation as a sort of pulse of incoming photons. A pulse distributed on a nice sphere of incoming photons. In this picture here, they come in from light like infinity. So here's the pulse. Let's draw the pulse of incoming photons. Arranged around, let's put it a little bit later. Let's make it a little bit later. Put it up here. There's the pulse of incoming radiation. It forms a shell. Where is the interior of the shell? At any given instant, where is the interior and where is the exterior of the shell? So that's easy. Here's a line at constant time, space. Where is the interior of the shell? The interior of the shell, in other words, the interior region, interior to the shell, that's the part of the space-time that's inside the shell near r equals 0. The part of the space-time that's outside the shell is out beyond the blue line here, and it's out here. Here's the incoming shell, and what does Newton's theorem, or the general relativity version of it, say? It says that on the interior of the shell, that's everything in here. Everything in there is flat space-time. In other words, it's correctly represented by the space-time that we drew here, which was just a representation of flat space-time. All right, so first of all, in the interior of the shell, which is to the lower left here, the space-time of just the flat Penrose diagram is the correct representation of everything that's going on. Right? Now, what about out here? Out here, we're told that there's a gravitational field. The gravitational field does not look like flat space-time, so this region out here is wrong. This is not the correct representation of the physics or the geometry of this infalling shell out beyond the shell. What is the correct representation? The correct representation is the Schwarzschild black hole. So let's redraw the Schwarzschild black hole to get rid of all the junk on it. Just redraw it. I lost my black pen. Oh, there it is. Okay, so here it is. And now somebody on the outside throws in the shell. The shell comes riding in, and what does it look like? It looks like this. Oh, I used blue before. Well, all right, let's use red. Here's the incoming shell. It comes in, experiences nothing special at this point over here, and just keeps going, but eventually, and it's a light ray. It's a light ray, a radially incoming light ray. It must move on a 45-degree angle. It moves in and just eventually hits the singularity. All right, so that's what the light ray would look like on the Schwarzschild geometry. But now, which part of the diagram is correctly representing the physics that we're doing? The interior of the shell is not correctly represented by the black hole. The interior of the shell is correctly represented by flat space-time. It's the exterior which is correctly represented. The exterior is out here. We can make it a little bigger, just to, I didn't mean to slice it so thin. Let's make it a little bit bigger. That just means the shell starts in earlier. The orange part here is the correct description of the space-time of the infalling shell, and the interior in here is not correctly represented. So how do we put these two together? How do we put these two together in order to make a single geometry? And it's pretty easy. You just take the wrong part of this and throw it away. And you take the wrong part of this and you throw it away. And you take the two right parts and sew them together, or glue them together, along the joining line where the infalling shell is. You take this, you put it up there, redraw it, and it looks like this. Let's see if we can see what's going on. All right, you see I've taken this diagram over here and simply placed it on top of the flat space-time drawing so that the shell matches across them. The shell is the thing they have in common. The infalling shell is the region that the two of them have in common. And on one side, you plaster the black hole geometry. On the other side, you put in the flat space geometry. That is the geometry of a black hole that is formed by an infalling shell. Okay. Now, excuse me while I consult with Newton. Any questions about this?
If you have a shell of matter like that collapsing, is there any kind of discontinuity when it crosses the Schwarzschild radius?
Mm-hmm. No discontinuity. But we're going to put that in and see where it is. Mm-hmm. No, nothing special happens. Okay. Where is the horizon? Where is the point of no return? Where on this diagram is somebody doomed? What you do is you start up in that corner there. That's the corner where the singularity appears to meet Scri plus. That's infinitely far away, so don't worry about it. Scri plus is very, very far away, very, very late time. But now run a 45-degree line from there down. It's not a place where anybody gets hurt if they fall through it. It's just a place where if you do fall through it, you cannot escape from the singularity. You will hit the singularity. If you're on the outside of it, here, you can get away. You can escape to Scri plus, for example. But notice something very, very curious. Even over here, you're doomed. You're still in flat space-time. You're still in flat space-time. The shell hasn't even gotten in yet. You can't see the shell. If you look backward on your light cone, you'll not see the shell. The shell is coming in at you at the speed of light. Light hasn't gotten to you yet. You don't know the shell is coming. And yet, if you're standing over here, in other words, if you were somebody who was just falling over here, just in free fall over here, you're already behind the horizon, even though the shell hasn't even gotten in yet. You're still in flat space-time. Not only don't you feel anything drastic, you don't feel anything. Nothing coming at you, but nevertheless, you're doomed. You're doomed, you cannot get out. So the horizon extends all the ways back to here.
Does that mean you can't cross the horizon or you can't cross the shell?
No, you can cross the shell.
As long as you're outside the horizon.
This is inside the horizon.
What happens when the horizon is inside the shell? You know, it hasn't collapsed down to the Schwarzschild radius.
When the shell hasn't collapsed,
Well, it hasn't reached the
it's over here.
Schwarzschild radius.
Here.
Right over here is where the shell crosses the Schwarzschild radius. Okay, so let's go back and draw a picture. Here's the incoming shell. It has a certain amount of mass. Associated with that mass is a Schwarzschild radius. All right, so there's some massive shell, mass meaning energy. It's made of light, but it still has energy, therefore mass. And here is the Schwarzschild radius of a black hole with that mass. If we had a black hole of that mass, it would have a Schwarzschild radius that's that big. As long as the mass is on the outside, Well, we can say that the mass is on the outside. That's all there is to say. But once the light crosses past the Schwarzschild radius, it's trapped. It cannot get out. It has formed a black hole for sure. Where does that form on here? Okay, right over here. Here's the infalling shell. It crosses the horizon right over here, and then it's on the inside, and there's no way for that shell to change its mind and get back out. Out here, the shell could change its mind and accelerate back out. Well, I suppose shells of photons don't have minds, but if they had a mind, the photons could turn around over here. Once they get past here, they cannot turn around. They can try to turn around, but they won't get very far. They'll hit the singularity. So this is the point at which the shell crosses its own Schwarzschild radius. Yeah.
Is there a meaning of the word horizon until it gets past that point?
Yeah.
It still means something?
Mm-hmm.
Just a distance.
The definition of the horizon is the place which separates those people who can get out from those people who can't get out.
But can't they get out before the collapsing shell crosses the distance?
Yeah, they'd be down.
No. Look at the picture. If you're over here, the shell hasn't crossed. Well, what do you mean before? Pick a time
Well,
coordinate.
this diagram you
Yeah.
drew over here,
Mhm.
if I'm inside the horizon, it's flat space, there's no gravitational field, why can't I just walk across?
Or shine a light?
Or,
Because by the time you get to here, the shell will have,
depends if you're at the top left or
yeah.
bottom.
I think the only answer is to look at this diagram. You look at this diagram and you say, I'm over here, I'm going to try to get out. But by the time you've gotten out, by the time if you can't get out, you simply can't get out, you have to exceed the speed of light. The diagram is the whole story. There's no more story than that. If you're here, you can't get out. If you're here, you can get out. So the horizon has materialized before the shell has actually gotten into its own Schwarzschild radius.
So what's the explanation of at least what I think is an apparent paradox, where inside the shell there's no gravitational field, there's flat space-time, why can't I just walk across the radius?
What do you mean walk? Here's walking. You're walking with the speed of light. It's pretty fast walking.
I mean, the shell's collapsing with the speed of light.
It is?
If it's a lot farther away from the horizon than you ought to be able to beat it. Right?
Here's it. Here it is.
Yeah, what that's saying is that if
No.
we're sitting here and a light shell is 1,000,000 miles away, we
Right.
are doomed.
Hmm?
If a light shell is 1,000,000 miles away, we are still doomed.
Right.
If it's coming this way.
Right.
Because we cannot walk that little distance.
That's right. You can't walk fast enough to get out of its way. If that light is coming in at you, you may be trapped even though you don't know that there's a light ray coming in. So the proof is the diagram.
Would this be analogous to, if you look at the, what do they call it, the radiation from the Big Bang, I forget what it's called, but it's radiation coming towards us.
Yeah.
But we can't get past it. Is that analogous to this?
It's analogous, but with a different analogy than yeah. But that's not a shell coming in. That's not a shell coming in. Right. Okay, so the horizon is a funny thing. It actually forms before the material gets past the Schwarzschild radius, and its definition is it's the point of no return. It is the point which, if you're on this side of it, you can't get out. If you're on that side of it, you can get out. The point, it's not a point, it's a sort of cone.
Question?
Yeah.
So if there was a mirror right at the outside of the Schwarzschild radius, and the light comes in, hits the mirror and turns around, bounces back out, what would that diagram look like?
Oh. Well, not likely you can really do this. You're saying, supposing there was a mirror right outside here.
With no weight, infinite reflection.
Well, I think the point is you can't have a mirror that has no weight. If you could, now, surely you can do this to some extent. You can build a mirror around a region like this, and the light ray would reflect off. If you really succeeded in building a mirror, the light ray would reflect off, and it wouldn't,
So it's turned 90 degrees right there
Yeah.
and hit time like infinity, right?
yeah, you wouldn't have a black hole. Yeah, so we can draw it on here. Here's the mirror. The mirror is at a certain distance away from the horizon, or away from the center. There's the mirror. Light comes in and bounces off. And that's all that happens.
So it's kind of not until it actually crosses the horizon that you're committed to being inside the horizon.
Yeah. That's right.
Question?
Yeah.
Just to test my understanding.
This light could decide to turn around at this point. But there's no way that this gentleman over here could tell that light to turn around over there.
But he could make a mirror really fast. But he could make a mirror really fast.
Not over here he can't. If he's over here, he can't get the material out for a mirror over here. He could have made a mirror in the past. He could have made a mirror in the past and protected himself. Well, let's see, can he? Yeah, maybe so. If he was over here coming in, he could decide to shoot out a mirror and have that light ray reflect off the mirror over there. But once he gets past this point, once he gets past that point, he cannot shoot out the mirror out to this point. He can't get it out there in time to rescue himself. Of course, in practice, he wouldn't even know that that light ray was coming in. Well, he might know. He might know. He might have. Bob could be, or let me get Alice. Alice is the one who always goes in the black hole. It's a convention. I didn't invent it. Alice goes in the black hole, but up till this point over here, she's together with Bob, and they're having a conversation, and she tells Bob, look, I got an idea. I want you to go out there and then shoot in a shell. And this is going to be a lot of fun. I'm going to get trapped behind the horizon and annihilated at the singularity. And in fact, I know that that's going to happen even before I can see this shell coming at me. So isn't that interesting? So she could arrange with Bob to contrive to send in that shell, know that it was going to come in, be over here, but once she gets over there, it is too late for her to do anything about it. She can't get a mirror out there. She can get a mirror over to here, but getting it over to here is no good. Everything's behind the horizon already. Anything back here will hit the singularity. She's got to get the mirror out to here. She can't do it. So,
Actually, I'm curious about what happens to if the mirror is inside the horizon. The mirror seems to, it has to get annihilated.
yeah, the mirror will just hit the singularity.
The
The mirror is just another thing which is doomed.
light will overwhelm any structure that had been built
Yeah.
there when it was flat space-time.
You could build a structure over here, well, let's say a structure over here, which reflected light. So that light coming in here would hit the structure, reflect off, and go into the singularity. Mirror, Alice, light, all of it winds up on the singularity.
So the singularity actually at a particular time, or is it like infinitely far away?
No, it's not infinite. It's not infinitely far away. There's a finite amount of proper time between here and here.
But it's, what about at the corner there?
The corner there is infinitely far away, but only the corner. Only the corner, right. But the implication is that somebody falling through the horizon has a finite amount of time to survive. Well, they could try to accelerate like mad once they pass the horizon over here and try to save themselves by sticking to that corner. The problem with that is that it would take an infinite amount of acceleration and an infinite amount of energy to make that much of an acceleration. You basically have to accelerate yourself up to the speed of light. So once you cross there, you're doomed. But you could last a long time if you could accelerate hard enough. Actually, that doesn't work. The more you accelerate, the less time you experience. That's the time dilation. Doesn't work. Doesn't work. But yeah, no, I take it back. Your best strategy is to stand still and just accept your fate.
Question?
Yeah.
Just to make sure I understand, so if there's this shell, let's say it's a million light years across, no matter what its mass is or its energy equivalent to mass,
Yeah.
that thing, if it's going inward, it's
Right.
going to form a black hole at some point.
Yeah.
Correct? And if I'm inside that thing, but I'm far enough away from its eventual center, then I can just hang out here and there's not going to be a problem. Is that right?
Sorry, you're at the center of it?
No, I'm not at the center. I'm inside of.
Inside the shell.
I'm inside the shell, but far away from the center, the eventual center.
All right,
Then,
well,
then
very-
I can just. There's no problem for me.
Depends if you're considered outside.
No, you're inside the shell before the shell crosses the shore. Yeah, then
I can just hang out, no problem.
well, yeah, you can just hang out and let the shell cross you. Yeah, absolutely. Yeah. Of course, the shell might hit you and make some damage, but that's a separate issue.
Is transforming that coordinate system to this, would this be analogous here in a particular point in time, whatever that means?
That's a
in this
point in
picture?
time. This is a point of time, this picture,
Would,
some point of time.
would it relate that the distance from the shell to the event horizon is greater than the event horizon to the person in between? Is that a different way of looking at this picture? So no matter how fast he accelerates to the eventual event horizon, he can't get there in time before the shell comes in.
All right, so let's ask about what the relationship between these pictures are, I don't know. Maybe I should draw it bigger. Let's draw it bigger and understand. No, we can do it over here, right over here. All right, so here's our Penrose diagram for the formation of the black hole. Here's the horizon. Here's the infalling shell. And the infalling shell hits right over here. Okay. Now, in order to speak of an instant of time, which time do we use? Time is just a coordinate. We can make coordinate transformations. An instant of time really means you pick a surface. You pick a surface which is everywhere space-like. You pick a surface, here's a surface, here's another surface, but you could pick it in various kinds of ways. Here's another surface. And these series of surfaces define a time variable. Time is one value on here, another value on here, another value on here, and another value on here. If you follow the time, at this time over here, there's a shell far away. The shell is far away. No horizon has formed yet. So this point has not been reached yet. A little bit later, the shell is still outside the horizon. Right? You're inside. You're in here. This point over here corresponds to the position of the shell, and so far nothing has formed on the inside. Well, there's a horizon over here. There is a horizon. At this point, right over here, at that time, right over there, that's the time at which the shell passes its own Schwarzschild radius. It's the time that the shell passes into the interior of the horizon. Here's the horizon. Shell passes into the interior, and once that happens, it can't get out. Okay?
So the Schwarzschild radius grows larger and larger. as
What's
time
that?
goes on. The Schwarzschild radius grows larger and larger, right? You got goes up that way.
Oh, yeah. You're talking about this. Yeah. It's not the Schwarzschild radius. Schwarzschild radius is by definition always the same thing, but the size of the horizon. Right at this point here, the horizon starts. Okay. The horizon starts very small. Only if you're in right near the center here are you doomed. If you're out here, you still get a chance to get away. That corresponds to being here or here. is a little tiny horizon has formed. The little tiny horizon has opened up. If you're in here, you're dead. If you're out here, you got a chance. All right, same thing here. If you're in here, you're dead. If you're out here, you got a chance. And then, without the shell having even gotten to you yet, the horizon starts to expand until it gets to this point over here. At that point, the shell crosses it. At that point, the incoming shell crosses the growing horizon. And past that point, the shell is on the inside, the horizon is on the outside, and
It's apparently still growing. And it should stop growing afterwards, right? I mean, why is it still growing?
why is what?
Schwarzschild radius.
Stops growing.
It should stop growing, right? I mean, why would
It does stop growing. It stops growing right at that point.
And above it is constant. Above it is constant radius line, is it?
Yeah, this is a constant radius line, that's correct. Doesn't look like it, but it is. Yeah.
Could you draw an observer who's sitting at half of the Schwarzschild radius on that diagram? You know,
Yeah,
stationary at half the Schwarzschild radius?
yeah, well, all right. Yeah, at some point, it just crosses the horizon. It's half the Schwarzschild radius and crosses the horizon.
But I thought he wouldn't experience any gravity until he passes through the shell. Until
He doesn't experience any gravity until he crosses the shell. But nevertheless, he's dead. I mean, he's not dead yet. He's not dead yet. Nevertheless, it's too late for him to escape.
there's no gravity until that.
Right. Crossing the horizon does not mean that you sense any sudden gravity taking place. That only happens when you cross the shell. But when you cross the horizon, you know what that means. That means you simply don't get away. You can't get away. So in that sense, the horizon is a little bit ghostly. That doesn't have a material significance in the way the shell does. Somebody falling through it doesn't experience it. In fact, down here, somebody falling through it, there's nothing there but flat space. Nevertheless, from that point, cannot travel fast enough to escape the fact that that shell is coming in. Yeah.
But this says then that if you start out early enough and you move faster than the shell grows,
Then the horizon
as
grows.
the horizon
Yeah.
grows, then you can escape.
That's right.
Your velocity has
That's
to be
right.
greater than the.
That's right. From here you can escape. From here you can't escape.
But your velocity has to be greater than the growth of the horizon.
Well, yes. But that's correct. But you don't see any horizon opening up at you. Yes, that's right. You'll have to. That's right.
But there's a much simpler way of kind of envisioning it. You have two shells. If the distance between the observer to the inner shell is larger than the inner shell, which is the horizon shell, to the radiation shell, no matter how fast he goes, he can't get to that point before they cross. So he's doomed. That seems a much simpler way of envisioning it, I think. That seems clear to me. This is coordinated. This warped my brain.
You try to do a calculation with that and find out where, for example, a horizon forms. Try to do that. You'll find you can't do it, and you wind up drawing the picture, taking this line, going backward to that point, and saying that's where it is. I know. I mean, right. I assure you, if you want to get a good picture of what's going on, the way to do it is to become familiar with these diagrams. If you try to reason it out without a good picture in front of you that accurately represents the relationships between the different parts here, and when the relationship, the important relationship, incidentally, is not the relative size of things. Here, there's a huge region of space and time up in this corner here. It's huge, infinite. The same little circle over here might be a tiny little region. So these diagrams are not correctly or, faithfully representing size scales. What are they representing? They're representing the motion of light rays. And in representing light rays, they're representing what things are in causal relationship to other things. What signals can propagate? Who can send a signal to whom? Can a signal from here get from Allison here, get to Bob out here? It reflects, the technical language would be that it reflects the causal structure, cause and effect. Cause and effect mean what can influence what. And the rule is a thing can only influence the things in front of it where light can get to. It cannot influence the things outside the light cone. So these diagrams were intended, they were built, first of all, to be able to draw everything on the blackboard, and second of all, to reflect faithfully the causal relations. What causes and effects, who can send signals to whom, who is trapped if they're stuck having to go slower than the speed of light. Those things are correctly reflected here. And so for that reason, these diagrams are very valuable. I can't think without them. I can't, if I have to answer a question of the kind you're asking, I have to draw the diagram. And the diagram says things much more clearly than trying to picture. I can't do it. I simply can't. I can't guess whether my guesses are right. I can't tell whether my guesses are right or wrong until I've drawn the diagram. Okay.
How long did it take you to be able to be comfortable and intuitive with these diagrams? Because at first glance, it's a little odd.
Not long. Not long. Just play with them for a while. Yeah. No, not long. Yeah.
So this is sort of the opposite of what you said in quantum mechanics. Instead in quantum mechanics, you can't think of it in terms of pictures. You have to go to the mathematics to understand it.
Yeah.
And here you're saying.
Yeah. But keep in mind, I mean, these are, in a certain sense, these are abstract diagrams. But you're right. I mean, you're right. That's absolutely right. General relativity is classical physics, and it can be represented, it can be drawn, it can be even pictured to some extent. All right, it's not so easy to picture four-dimensional curved space-time, but that's hard, yeah. But still, you can go a lot further in visualizing it than you can quantum mechanics. I think that's right. I think that's an interesting fact. Quantum mechanics is much more abstract in that sense. Okay, we're going to quit a little early tonight.
For more, please visit us at stanford.edu.